So in the last video, we talked about Newton's first law, which was essentially an object in motion will stay in motion and an object at rest will stay at rest unless an external force is applied. So in this video, we're going to consider what happens when an external force is applied, and in doing so, we will define Newton's second law. So let's consider a scenario. Let's say that I'm, going to kick a soccer ball. And let's say on my first kick, I don't try too hard. So I don't exert a bunch of force on the ball. And let's say that, it travels some distance and lands here. Okay. Now let's say that on my second try, I exert a lot more force. Okay. So a lot more force. And let's say that now the ball does something like that. Okay, so we see it goes a lot further, but really more importantly is that it accelerates more because I've exerted more force. So it's moving faster, and then in doing so it's moving further. So I can say that as I increase my force, the force applied, I also increase acceleration. So force and acceleration are directly proportional. So I can write this statement. Acceleration is proportional to force. And that squiggly line in the middle means proportional. So they're not equal to each other, but they are in proportion, meaning that when one increases, the other increases. And when one decreases, the other also decreases. Okay, so let's consider another scenario. Let's say that I have a soccer ball and a bowling ball. And let's say that in both cases, I kick the ball with 2 newtons of force. So the force is constant. Now, intuitively, you would say that the soccer ball would move faster and further than the bowling ball. In fact, the bowling ball might not move at all. It might hurt my foot by trying to kick it. Okay, so what happens there? So we see that the mass of the soccer ball is a lot less than the mass of the bowling ball. And the soccer ball accelerates more than the bowling ball. So we see that mass and acceleration are inversely proportional. So I can write this statement. Acceleration is inversely proportional to mass. So when mass increases, acceleration decreases. And when mass decreases, acceleration increases. Okay, so putting this all together, we get that Newton's second law is acceleration produced by a net force is directly proportional to the magnitude of the force and in the same direction as the net force and inversely proportional to the mass. What this means is this first part about directly proportional to the magnitude is saying that as I increase the magnitude of the force, the acceleration of the object will increase. The part with the direction is that, if I kick a ball to the left, it's not now going to accelerate to the right. It's going to move in the same direction as the force. And then it's inversely proportional to the mass, meaning that as mass increases, acceleration decreases, and vice versa. So from there, we can write an equation for acceleration. And we get that acceleration is equal to F, force, over mass. You've probably heard F equals ma. It's kind of a common phrase. And you get that just by multiplying mass the other side, but it's all based off of Newton's second law. So let's now consider an example using free falls. So we said earlier that in the case of a free fall, the time that it takes an object to hit the ground is independent from the object's mass. So if I have another object, let's say, that's twice as big as this, but they're dropped from the same height with the same initial velocity, they're going to hit the ground at the same time, as long as we can neglect air resistance. Okay. So that is because the only force acting on a free fall is gravity. Remember that gravity moves downwards and is a constant of 9.8 meters per second per second. So let's do out a sample problem. let's say that I have, again, two balls. Okay, and let's say that the mass of ball number 1 is 10 kilograms, and the mass of ball number 2 is 20 kilograms. So let's figure out the acceleration of ball number 1 and ball number 2 using the formula we just found. Acceleration equals force over mass. So remember when we're talking about free-falling objects, the only force acting on the ball is its own weight. And remember that weight equals the mass times acceleration. So the weight of ball number 1 is 10 kilograms times acceleration, which is 9.8. So that equals 98 newtons. And the weight of ball number 2 is 20 times 9.8, which equals to 196 newtons. Now, when I plug in to find the acceleration of the ball, well, again, acceleration is force divided by mass. The force is 90 newtons divided by the mass of ball number 1, which is 10 kilograms. So I get 9.8 meters per second squared. And in the second scenario, I also get 9.8 meters per second squared. It's 196 divided by 20, which is 9.8. Okay, so we see that regardless of the mass of the ball will still fall at a constant acceleration of 9.8, which we already knew, and this formula just confirms that. We can summarize this by saying that twice the mass produces twice the force, okay? So we see, I'm just going to put it down on the bottom, twice the mass produces twice the force. So you end up with just the same force over the same mass, which is a constant acceleration. So at this point, you might be thinking, well, I know that things drop from the same height don't always hit the ground at the same time. If you consider the case of a feather drop from the same height as a baseball, you would probably see the baseball hit the ground before the feather hits the ground. And that's because in the real world we have air resistance. So air resistance kind of works in the opposite direction as gravity. And in the case of the feather, a feather is really light and has a lot more surface area than a baseball. So air resistance can kind of build up underneath the feather. And what happens in that case is air resistance ends up equaling the weight of the feather. So acceleration upwards and downwards cancel, meaning that there's no net acceleration, and the feather reaches a constant velocity, and this is called terminal velocity. So now the feather is no longer accelerating, it's falling at a constant velocity down, while the baseball is still accelerating and starts to move faster than the feather, and therefore hits the ground before the feather. So there are a bunch of factors that play into air resistance. One of them is mass. Lighter objects build up air resistance quicker than heavier objects. Think of heavier objects can kind of plow through air really effectively. Surface area. So as surface area increases, there's more area for like air to build up underneath the surface. So in that case, air resistance builds up faster. And then also objects falling at like slow speeds tend to build up air resistance slower than objects falling at fast speeds that are in contact with a lot of air that can kind of quickly build up underneath the object. So in all of these cases, air resistance does affect the velocity and acceleration of the object falling. And that's why in the real world we do see objects falling from the same height hitting the ground at different times. But without air resistance, or we can neglect air resistance, all of what we've talked about holds true. So that's just a side note for Newton's second law, and in the next video we'll talk about Newton's third law.